Hello! Today we are continuing in our GCSE physics revision series and we're starting a new subject in electricity. Today we're going to specifically be considering static electricity. Electricity is all to do with electrons. Now we'll learn more about what electrons are when we do atomic physics, but for the moment it's sufficient to know that an atom consists of a central nucleus, which is positively charged, and orbiting electrons. There are different numbers of electrons, which essentially orbit in a kind of the way that the Earth orbits the Sun, although not quite like that. But that will do us for these purposes. And there is the same charge on the electrons are charged and the nucleus is charged. This is charged positively, this is charged negatively. And the combination of the two, the charge on the nucleus and the charge on the electron, are usually equal and opposite, which means that the entire atom is neutral. But you can, if you give this electron enough energy, you can cause it to shoot off out of the atom. And if you do that, you then have a free electron. And it's those free electrons which are the source of electricity. Of course, if you take an electron away and an electron is negatively charged, you will leave behind an atom which is marginally positively charged because it was neutral. You've taken a negative charge away, you'll leave a net positive charge. So if you take electrons away, you leave positively charged atoms behind. Now I said that both electrons and nuclei are charged. Charge is a feature of a body. It's a bit like mass. Mass is measured in grams, temperature is measured in degrees centigrade or sometimes Kelvin. Charge is measured in units called coulombs. And the charge on any one electron is very small. Rounding, it's 1.6 times 10 to the minus 19 coulombs. And just to remind you that 10 to the minus 19 is the number 1 divided by 1 followed by 19 noughts. 1 divided by 10 million million million. That's very, very small. So the charge on an individual electron is very small, but there are billions and billions and billions of electrons, and together they can constitute a large charge. If electrons sit on a substance and don't move anywhere, that's called static electricity, because they don't move. If, on the other hand, electrons flow through a substance, then that's obviously moving electrons, and that is electric current. Now, there are 3 types of material in the world. There are what we call insulators and conductors. Conductors tend to be metals. The difference between the two is that electrons do not easily move through insulators. In fact, for all practical purposes, they don't move through them at all. You can put an electron on an insulator, but it won't go anywhere. Whereas with conductors, electrons can move through conductors, like copper wires, and when electrons move through conductors, that is the process of electricity. There's a third type I told you about, and that's called semi-conductors. What that means is that the electrons can flow through semiconductors, but not as well as they flow through conductors. Electrons, very many fewer, are able to flow through semiconductors. And it's the nature of semiconductors, which we may come on to a little later in this series, it's the nature of semiconductors that gives rise to things like transistors and diodes. And they are obviously critical to many electronic circuits that you have in your computers, your mobile phones, your cameras. Virtually all our electronic equipment today relies heavily on transistors and diodes, which are themselves based on semiconductor technology. In this approach that we're going to be looking at, we shall only be concerning insulators and conductors. When we look at insulators, we'll be looking at static electricity because the electrons don't move. when we look at conductors, we'll be talking about moving electricity, moving currents. Today we're talking about static electricity. If you take a polythene rod, and polythene is an insulator, so this is polythene, and you rub it up and down with a duster, what will happen is that some electrons are transferred from the duster to the polythene. And that will leave the polythene with a net negative charge because electrons are negatively charged. So rub it up and down and electrons transfer to the polythene rod. Take the duster away and you've got a net negatively charged polythene rod. By contrast, if you take something like an acetate rod and you rub it with the duster again, rub it up and down with the duster, what will happen is electrons will be taken off the acetate onto the duster, and if you take electrons away, as I showed a little while ago, if you take the electrons away from an atom, you leave a positively charged or a net positively charged atom behind because one of the electrons has been taken from a neutral atom, leaving a positive charge. Please note, it is always the electrons that move, never the positively charged atoms. So in this case, the electrons are transferred from the duster to the polythene. In this case, the electrons are transferred from the acetate to the duster, leaving behind net positively charged atoms. I spoke about insulators and conductors. Conductors conduct electricity, insulators don't. And that's very important, for example, for the cables that you use to convey electricity. A cable will typically consist of a central core, which is usually made out of copper, which is a metal and is a conductor, and electrons will happily flow along that cable. And that's called electricity, that's an electric current. But if you were to touch that copper cable, you are in danger of getting an electric shock because then the electrons will travel through you. So what you find is that surrounding that copper cable will be some kind of plastic material which is an insulator, and the electrons do not flow through that. So if you happen to touch the cable that is connecting the plug to your iron or the plug to your kettle, that is safe because the insulator around the copper cable does not conduct electricity, so no electricity can flow through it. Whereas in fact there is a very high, if we're talking about kettles or irons, there's a very high current flowing through it that would do you a lot of damage if you touched the bare copper wire. So it's always important to check that the cables that connect your plug to your appliance, particularly if it's an appliance that uses a lot of current, make sure that they are not broken or fractured in any way, because that can be very dangerous. If they are, they need to be replaced, and replaced by somebody who knows what they're doing. Now I want to introduce you to a little phrase that you will hear many times in physics. Like charges repel, unlike charges attract. What I mean by that is if you bring two negative charges together, they are like charges, so they repel. There is a force that pushes them apart. Similarly, if you bring two positive charges together, they are like charges. They are the same. So there is a force that will just cause them to push apart. But if you bring unlike charges, a plus and a minus together, then the force will cause them to attract. Unlike charges attract. Like charges repel, unlike charges attract. And although you do not need to know the nature of the force that's doing that, I'm going to tell you anyway so that you understand it. If we bring two charges, let's make them opposite so they will attract. So we'll have a charge of plus Q1 on here and we'll have a charge of minus Q2. They don't have to be the same size charges. There can be several charges on one and a different number on here. So the total charge is plus Q1 coulombs on this one. a total charge of minus Q2 coulombs on this one. They will attract because they are opposite charges. And let's say the distance between them is a distance r, then the force that is causing them to attract is going to be a constant, which we don't need to worry about, times the charge on one times the charge on the other, which is a negative charge, we just need to remember that, and that makes the force an attractive force, divided by r squared. So in other words, the force is directly proportional to the size of the charges. If the charges are greater, the force will be greater, but it's what's called inversely proportional to the distance between them. As the distance between them increases, so the force will decrease. If you take these charges a long way away, the force between them will be smaller. If you bring the charges very close together, the force between them will be very much more increased. And you may recognize that formula. It's not a million miles away from the formula that I showed you for the gravitational attraction. In the case of gravity, the force was equal to G, which was the gravitational constant, times the mass of one body times the mass of another body divided by r squared. So they're very similar. This is the electric force, which relates to charges and their distance. This is the gravitational force, which relates to masses and their distance. So you might be tempted to say, surely, when you've got two bodies, each of which will have a mass, electrons have masses, if you've got two bodies, surely there will not only be an electric force between them, which is given by this, but there'll also be a gravitational force, and it's an attractive gravitational force, always attractive with gravity. It'll be an attractive gravitational force between these electrons. Doesn't that have an effect? And the answer is not in the slightest, because the ratio of this force to this force is positively huge. This force is orders of magnitude bigger than this force. This force is trivial compared to this one. You can ignore this force when there are electric forces that you need to take into account. So now I can explain the balloon on the wall trick. I don't know if you've ever done this at a party, but if you take a balloon, one that's blown up, you tend to have to do this on a dry day. If there's moisture in the air, it doesn't work so well. Moisture and electricity are always a bad thing. So you take a balloon and you rub it on the side of your jumper. Now that is, since a balloon is made of a kind of polythene type of material, and your jumper has the same effect as the duster, then rubbing the balloon on your jumper is the same as rubbing the polythene with the duster, and that bestows from your jumper electrons onto the surface of the balloon. So there will be an excess of electrons on the side of the balloon that you rub against your jumper. Now let's say you bring that against the wall of your room. When you bring the balloon with an excess of electrons to the wall, the electrons, the free electrons that are in the wall, and there will always be some, they will be repelled because like charges repel. So the electrons will all go to this side of the wall. And if they do that, they will leave behind positively charged atoms, because the atoms that used to have those electrons have now had the electrons taken off of them, and they've moved away because they repel, because the two charges are alike. But now you've got a negatively charged balloon and a positively charged near wall. And so there will be a force of attraction between the two. So if you take the balloon and you place it on the wall and leave it there for a couple of seconds, then take your hand away, you'll find that the balloon sticks to the wall and won't actually move. There's nothing holding it up, apparently, but it will just stay there. And it's staying there under the electrostatic attraction between the electrons, the surplus electrons on the balloon, and the net positively charged atoms that have been left behind on the wall, because the electrons in the wall have been pushed away because they have been repelled by the electrons on the balloon. Of course, if the charges are too high, you can get something fairly dramatic. let's suppose that we have a polythene rod and an acetate rod. This is the polythene rod, this is the acetate rod. We've rubbed them both with a duster, so consequently the polythene rod is now net negatively charged and the acetate rod is net positively charged. There's an attraction between the two, but what will happen is that these electrons will be very keen. Remember, it's always the electrons that move, never the positive charges. The electrons will be very keen to get at the positively charged particles, and in their eagerness, you may well see them shoot across in the form of a spark. And that's exactly what happens when you see a spark. The electrons from a surplus negatively charged unit are jumping across to neutralise, as it were, the positively charged atoms in another thing. Let me give you some examples that you may have experienced. When you comb your hair, you're using a plastic hair, usually a plastic comb, and your hair will have the same effect as the duster. That will put excess electrons on your comb, and at some point they may jump off, and so when you're combing your hair you can quite often hear little sparks. When you take your jumper off, if you're wearing, say, a nylon shirt, that jumper will put electrons on the nylon shirt and they in turn will jump off. Quite often when you're taking your jumper off you can hear little sparks. That's what's causing that. Sometimes when you're walking along on a carpet, that carpet is essentially having the same effect as the duster because you're rubbing your feet on it as you go along and you're building up electrons on your feet as you rub them on the carpet, and then you grab hold of a metal door handle and you go ouch because you feel the spark jump across onto the door handle. It's a very tiny electric shock that you're getting. If you have too great an electric charge, of course that could be very dangerous. So we invent the concept of earthing, and we usually represent earthing in this way. What we mean is we take a big copper wire, copper being of course a very good conductor, and we have a big coil of it which we bury in the earth. This is all the earth. The earth can be regarded as a reservoir of electrons. There are billions and billions and billions of electrons in the earth, and a few more don't make any difference. So if you earth something, what you do is you convey all the electrons down into this huge reservoir where they're all perfectly safe, instead of them travelling through you down to Earth, which is not safe. So earth wires are often placed in so that in the event of a particular device, your hairdryer for example, if something goes wrong in that hairdryer and the hairdryer becomes live, what you do is you connect the hairdryer to the earth wire, and that earth wire goes out through the cable of your hairdryer and indeed through the whole of the circuitry of your house down to the earth where a big copper wire is buried, so that if the hairdryer itself becomes live as opposed to just the mechanics within it, instead of it going through you, it goes through the earth wire and down to earth. This is also the principle on which a lightning conductor works. You might have a house, and ordinarily the lightning would strike the house and could cause significant damage, but if you put a lightning conductor on the house which has a big copper cable that goes down the side of the house and buried in the earth, then what happens is the lightning strikes the lightning conductor, is carried away from the house and down to the earth where it's perfectly safe. Finally, for those of you who need to know it, and not everybody does, I want to tell you about the Goldleaf electroscope. Now, a Goldleaf electroscope is basically a piece of metal, flat metal, and a metal bar like this, to which you attach a kind of a little flap. And the flap is usually made of gold, though it can be made of other materials, and essentially that flap can, as it were, flip up, so it can just flip like this. It's a kind of hinge. This is a metal bar. This is a very lightweight piece of foil, so it's not very heavy, and it can, as it were, it's hinged so it can flip up. Now let's suppose that we bring a polythene bar which is charged, we've rubbed it with a duster so it's got a net negative charge on it, and we bring it close to the Goldleaf electroscope. What is that going to do? Well, like charges repel. So all the free electrons, this is a metal, so electrons can travel in a metal, all the free electrons that are in the metal will be driven away from the top because they will be repelled by this polythene bar. So all the electrons will go down here. And of course, in doing so, they will leave a net positive charge on the surface. And that positive charge, of course, is attracted to the electrons. And if you're not careful, you'll get a spark. So you mustn't come too close, otherwise these electrons will jump across. The real question is, what is going to happen down here in this bit of the Goldleaf electroscope? We've got two things that are both negatively charged. We've got the bar and we've got the very, very lightweight gold leaf. Well, light charges repel. So what you're going to end up with is the positively charged bit at the top, but now the gold leaf is going to flick up because those electrons on the gold leaf are trying to get away from the electrons which are on the main bit of the electroscope. So now, rather than simply hold the rod close to the electroscope, I'm now going to touch it. So I'm going to start off by touching it with a negatively charged rod. If I touch the electroscope with a negatively charged rod, what is going to happen is that some of the electrons are going to flow onto the Goldleaf electroscope, which is, of course, all made of metal, so the electrons will flow through it. So the electrons now will flow from the rod onto the electroscope and onto the gold leaf. And of course what that will do is to cause the gold leaf to move away, because the negative charges on the gold leaf will repel the negative charges on the base of the rod. Now if I take the rod away, the electrons are there. They're stuck. They can't go anywhere. The whole thing is now negatively charged, and because you've got these electrons, they are repelling one another, and so the gold leaf is permanently now at an angle. And you can use this to determine whether another rod, whose polarity you don't know, so you don't know whether it's negatively or positively charged, you can determine what it is, because suppose you bring another rod and we don't know, is it positive or is it negative? You don't touch this, you just bring it close. If you bring it close, if it is negatively charged, then what's going to happen is that more and more electrons are going to be driven down because they're going to be repelled from the negatively charged rod. So if it's negatively charged, electrons are going to be pushed away, so more and more electrons are going to be at the bottom, which means there's going to be a greater force, which means that the gold leaf will move even further away, and that tells you that the rod was negatively charged. What happens if the rod is positively charged? Well, now the electrons will be attracted to it, so they move up and sit on the top here. And they move away from here, so there are fewer electrons at the bottom, so there's less of a charge, there's less of a force between these two parts, and consequently the gold leaf moves down. It may not completely close, but it will move down. And that means that this rod was positively charged. So if you bring a rod towards the gold leaf electroscope but don't touch it, and that causes the gold leaf to move further up, that means that the rod is negatively charged because it's driving more electrons down here and thus increasing the force between the rod and the gold leaf. And if you bring a rod close to the electroscope but not touching, such that the gold leaf goes down in angle and goes back closer to the rod, that means that it must be positively charged because electrons are being attracted to that positive charge. There are fewer electrons down here, consequently there is less of a force between the two, and the gold leaf will slightly collapse. Of course, you can also charge a Goldleaf electroscope positively by bringing and tapping a positively charged rod, that would be the acetate rod. You actually touch it on the electroscope, and what will happen now is that electrons that are in this metal bar will flow into the rod. They are attracted to the rod. And if electrons flow into the rod, what will happen is they will leave positively charged atoms behind. Remember, it's always the electrons that flow, and they will flow also from the gold foil, so they will leave positive charges on the gold foil, and of course that will therefore mean that the gold foil will spring out, because you've now got two lots of positive charges which are going to repel, and so the gold foil springs away from the rod. And there's a third way of leaving the rod positively charged, or leaving the electroscope positively charged. There is the uncharged electroscope with the piece of gold foil. You bring a negatively charged rod close but don't touch. That of course will mean that the electrons will be repelled down here. And that of course will mean that the gold leaf will move out, because the two sets of electrons will repel one another, and it will leave positively charged atoms up here, because the electrons have been repelled from the top down to the bottom, leaving positively charged atoms at the top. Now, suppose, leaving the rod where it is, suppose you now touch with your finger the top of the electroscope. That is the equivalent of earthing the electroscope, because the electrons will now want to flow to Earth. So all these electrons will flow. It doesn't matter that they're going against the attraction here, they still want to do it. This is a route to Earth and they want to do it. So the electrons now flow to Earth, always the electrons moving, remember. So these surplus electrons are now going down to Earth and are lost. So what are you left with? You now take your finger off the electroscope, you take this rod away, and all you're left with is positive charged atoms, and they now spread throughout the electroscope. Or more accurately, the electrons move such that what you've effectively got is a distribution, an even distribution of positively charged atoms, including on the gold leaf, and that causes the gold leaf to spring out, because you've now got positive charges, like charges repel. So that's a second way, two ways of doing the leaving an electroscope permanently positively charged. One is to touch it with a positively charged rod. The other is to bring a negatively charged rod close by, so that you've got positive charges at the top and negative charges at the bottom. Put your finger on the top so that effectively you earth it, so you drain the electrons away. Take the rod away, and all you're left with now is positive charges, and that means that the whole thing is positively charged. And that means that the gold leaf will spring out, because the two sets of positive charges will repel.